All right, guys. So in this video, we're going to continue our discussion of the process or the limit process that we discussed last time. And we want to give an introduction of what a limit is. And first, let's work our intuition here and try to define what this limit is intuitively. And then we'll give a more formal definition of limit. A limit. So I want to start with an example here. We have this function f of x equal to x cubed minus x squared over x minus 1. So this is of course a rational function, and we want to try to graph it. And if you recall from your algebra course, we can factor this numerator and also the denominator. The denominator is already factored, but you can pull out an x squared here, factor out an x squared. We have x minus 1, and we can see how we have a common factor here. We want to go ahead and cancel out, so we really just end up with an x squared. Okay, so roughly, we get something like this. It's not perfect, guys, but we know we intersect the origin there. Now remember, this is not the exact same thing as the x squared function that we know of. I mean, it looks the same except for one thing. Here we cancel out a common factor, so we want to make sure that the original, right, the x equal to 1 is not in the domain. So then if you think about the parabola, it goes through here, but at 1 would be 1, 1. There's actually a hole there. Everything else looks the same. I mean, it's identical to the parabola except for that hole there. Here, if I wanted to ask you, okay, where is this function going as x approaches 1? As it's getting closer and closer to 1, where is this function actually going? As I'm coming from the left here, and also from the right, as I'm approaching this, as x is approaching 1 from the left or the right, where is this function going? Right, it's getting closer and closer to that hole there. Now remember, the function is actually not defined at that point. At 1 is not defined, right, because we said it's not part of the domain. But the limit doesn't really care about whether there is a function value there or not, if the function is defined there or not. It just cares about if it's infinitely getting closer and closer to something there, to some real number. So that's the question right here. Intuitively, we can say, okay, yeah, this is getting closer and closer to that 1. It's just we're never going to get there. Well, that's the idea of the limit. A limit is going to be basically, where is the function getting close to? Is it approaching a certain number, a certain real number, as x goes to this limit point? In this example is 1. So in this example, we sort of graphically, we can kind of make sense of it, right? Find that limit graphically. Okay, so this is our graph way to interpret it graphically. You can also try to do this numerically in the way. Now it's a little bit of work and a little bit tedious, but you can try to plug in numbers into your function, right? A few numbers before 1 to the left of 1, a few numbers to the right of 1, and again, guys, you can get as close as you want here. The idea is that this works no matter how close you are, right? And we're going to define formally what this word means. What does it really mean to be close enough? So, like for instance here, we know that 1 is not defined there, right? So it's undefined, but so the function doesn't exist there. Like the function does not defined right there at that point, but the limit may still exist. And how do we numerically? We'll show that if, well, before 1, I can always have, like 0.999. I can do 0, or I can start from 0.9 here, then 0.99, and just get closer and closer, as accurate as you want it to be. Same thing here. I can do 1.001. Now, of course, you have to put this in your calculator. You have to square our function is x squared. You have to square all these things. And then you'll see that these numbers are actually getting closer and closer to this one right here. This one right there. Okay, so you can see how after evaluating all those x's here, you can see, I mean, coming from the 2, you start with 4, but as soon as you start getting closer and closer to this 1, these numbers here start getting closer and closer to 1 as well, right? And also coming from the left, you know, so you start getting closer, you start, you know, the function was 0.81, right? That's not that, it's close to 1, but not that close, and then it starts getting better and then better. And if you get even closer, as x gets to get closer and closer to 1, that function is also getting closer to 1. So all of this takes us to the informal definition of limit, and we're going to use the following notation. So this is read, the limit of f as x approaches c is L. And again, L has to be a real number for the limit to exist, and this x approaching c means it has to approach from both sides. Having that in mind, let's look at some examples on when the limit doesn't exist, when the limit fails to exist here. So one of the conditions was that as this x approaches c, and when we said approach c, we mean from the left and right. That's one of the things that we had to make sure it happens for this limit to exist, that x approaches c from the left as well as from the right. So what happens if that doesn't happen? So this is where our first example is going to show. So in this first example, we have this function, it's the absolute value of x over x. And if you graph this, you're either going to get -1 or 1. So every time you plug in a negative value, you're going to get -1 from here. And when you plug in a positive value, you're going to get +1. So this is a typical example of a function where as x gets closer to 0, the limit doesn't exist here. So limit of f of x as x goes to 0 does not exist, since it's getting closer to a different number from each direction. So as you go from the left, it's getting closer to 1. As you come from the right, it's getting closer to 1. So from the left, it's going to -1, and from the right, it's going to 1. So no matter how close you get from each side, you're always going to be closer to 1 here without ever getting there. You do not have, there's nothing defined as 0. So this is like our first example where we don't really care about ever getting there, but you're not approaching the same number from both sides. So the limit of f of x as x goes to 0 from the left, and we represent that with a negative superscript there, is equal to -1. And the same way, the limit of f of x as x goes to 0 coming from the right is equal to 1, and these two are not equal to each other. So because the two-sided limits coming from the left and from the right are not equal, then the limit itself doesn't exist. So this is the example, or one example, of when this condition is not met, right? So in order for the limit to exist, again, it has to approach, x has to approach this limit point c from both sides. Now, the other example is if we don't satisfy the other condition, which is this limit, if it exists, has to be equal to some real number L. This L has to be a real number. So what happens when it's not a real number, when it approaches, in this case, infinity? If it's not a real number, it's going to have to be infinity. So here we have f of x equal to 1 over x squared. And if we graph this, it's another rational function, we get this following graph. And notice how if we were to take or find the limit as x goes to 0 again, of f of x. In this case, we don't have the problem that we had before where one-sided limit went to a different number. As x gets closer to 0 from the left and also from the right, notice how the function is going to the same place, which in this case is infinity. Infinity is not a real number. Therefore, this limit doesn't exist. Because the definition of limit says we have to be going to a number, to a real number. Right? It has to. This function has to be approaching a real number as x approaches this limit point c from the left and the right. So we saw what happens when we don't approach the same limit from the left and the right, then the limit doesn't actually exist if these two are different. But now we see that even if they're the same, but it is not approaching an actual real point, but instead is infinity. And this works also for negative infinity. Then we have also that the limit fails to exist here. That's the other case. And then there's one more case that may come up, and that is the oscillating behavior function. So this is an example, f of x equal to sine 1 over x. And the behavior of this function is as it gets closer to, again, 0. So here we're going to try to compute the limit of the function, again, as x goes to 0. So coming from the left and the right, it seems almost like it's going to the same point, right? We're approaching the same point, and it's not infinity. So you may almost think that there is a limit here, but in reality, as this gets closer and closer to 0, this keeps oscillating between -1 and 1. You'll get infinitely closer and closer to 0, and it'll keep doing that forever, oscillating between 1 and 1. So this is the oscillating behavior one. This is another one where the limit doesn't exist, because again, it fails to be a real number. Well, actually, it fails to approach any number, any one number, right, coming from the left and the right. So now the last thing I wanted to discuss is the formal definition. Now we've seen enough, I think, built enough intuition of what a limit is. There's going to be a more rigorous formal definition of the limit, and that's what I want to discuss. So here's a more formal definition of limit, and this definition is normally called the epsilon delta definition because we use those letters in here. And what it says is that we have a function f defined on an open interval containing c, except possibly at c. Remember, the function doesn't have to be defined at the limit point, as we saw in the examples above in the beginning. There could be a hole in there, but the limit could still exist as x gets closer to the c, to this limit point. And let L be any real number. The statement, what we've seen, the statement limit of f of x as x goes to c equal to L, means that for each epsilon greater than 0, so for each positive epsilon here, there exists a delta greater than 0, such that if x minus c, the absolute value of x minus c greater than 0 but less than delta, then the absolute value of the function of f of x minus L is less than epsilon. Okay, so I typically like to write it this way just for abbreviate some of these words, but basically what I've written here is the same thing that you see here. This is spelled out. This says, obviously we're assuming f is a function, all that, L is a real value, and if this function is defined over some open interval containing this c, except possibly at c, so meaning c doesn't have to be defined at f, okay? The limit can still exist, and it's saying this limit is true if and only if, meaning goes both ways. This symbol means for all, or for every, or for each, right? For each epsilon greater than 0, positive epsilon, this symbol means there exists delta greater than 0, there exists a delta, such that, this is another symbol that I use, such that what it says right here pretty much. The absolute value of x minus c is less than delta, implies that the absolute value of f of x minus L is less than delta. All right, so let's look at this example here. This is the first example that we had at the beginning, where we get the parabola, but there's a hole at x equal to 1. So we exclude that from the domain. So let's bring this back and try to apply the actual formal definition here. Now we know already that this limit does exist, even though there's a hole here at 1. We know that the limit as x goes to 1 of this f of x is actually equal to 1. Now, how do we use this the formal definition? What this definition is saying right here, this quantifier here says for every epsilon though. So how do you prove something for all numbers, all positive numbers? That's impossible because there's an infinite amount of those. So, but first, before we actually prove it formally, so we already know the limit is 1. Let's let epsilon be equal to 0.5. I'm taking 1 epsilon here, and I want to make sure this says this gotta be, in order for the limit to exist, this gotta be a delta greater than 0, such as this is true. If I choose, I'm gonna choose my delta. I'm gonna choose. So you only have to find 1 delta. There could be more than 1, but it's only sufficient to find 1. So we're gonna let delta be 0.2. Okay, so this part right here, this part is saying assuming I'm letting epsilon be 0.5, I'm going to choose a delta equal to 0.2. I'm saying if I go, this part right here says if x minus c is less than delta. So in other words, if I pick any x in this neighborhood of delta, so delta is 0.2, so this would be 1.2, and this will be 0.8. Right? So you're going 0.2 in each direction of 1, right? Because remember, your c, this is c. This is your c right there. Okay, so if you go 0.2 and pick any x from here, so any x in this interval, not including the 1, if we're guaranteed that any x that we pick here, any x that we pick in this neighborhood of delta falls in this green area here, and that's for every x in this interval, that proves that the limit exists. Now, notice here, I've just showed you that this is true for one specific epsilon, but how do we show this for all epsilon? So this is where a little proof will be needed to actually show for all epsilon. Okay, so let me show you a simulation here of what we were saying. Notice here, I have the same function here, the function we've been talking about, the parabola. And when you graph this in a computer calculator, you know, if you have that hole in there, you may not be able to see it. But that's not going to keep us from finding the limit. We already know that the limit does exist as x goes to 1 here from the left or the right, both, or the limit of the function is equal to 1. This approaches, it gets closer and closer to 1. You can see it right there. Now, this green area highlights the neighborhood of delta. So remember I picked my delta to be 0.2, and this orange area is highlighting the neighborhood of epsilon. So my limit is 1 right here, and you know I went 0.5 in each direction. That's my epsilon. And I picked a delta. I chose a delta of 0.2, and notice how the green just shows you that this delta does work. So I was able to find a delta that worked. And you can see here, look at, just follow the cursor here. Any point in here, in this interval here, 0.8 to 1.2, any point in there, not including the endpoints, except possibly 1, because remember there's a hole here. But you know, so we're not counting the limit point, we're just counting everything else. Like let's say if I pick the point here and I just go up, I go to the function curve, I'm in that orange area. I'm guaranteed to be in there. And you can see how all of this stuff ends up on the orange area. Now notice here, if I was to decrease the epsilon, this is supposed to work for every epsilon. If I decrease the epsilon, notice, as soon as this goes down here, it goes into the red because I can find an x here that goes outside the neighborhood of epsilon right there. So then I no longer are guaranteed to, you know. So in that case, if I have a smaller epsilon, look, if I make it smaller, I have to just be able to find a different delta. Remember, I only have to find 1. So obviously if I make it bigger, that's not going to help. I have to find a smaller delta. And as soon as I go down there, so 0.15 will do it. I mean, obviously anything smaller than that would also work, but I only need to find 1. This is 1.1. That would work as well. As you change this epsilon, you're going to have to change that delta as well to be able to make it work. But no matter what epsilon, that's what depart from the for all epsilons, that's what that means. No matter what epsilon you pick, no matter how small I make this, remember we can always zoom in here. No matter how small we make this, I can always pick a smaller delta and make it work. Okay, so how do we show that this definition works for all epsilon? So here's a simpler example here, just to show you how you would go about proving something like that using the definition, the formal definition. So we have that, we want to show that the limit of the function 2x plus 1, which you remember is just a line, as x goes to 2 is actually equal to 5. Right here, you know, since we're interpreting everything graphically, this would be your line 2x plus 1. As x goes to 2 from the right or from the left, the limit is going to be that 5. So how do we actually prove that? And again, I'm using this simple example just to show you how to go about proving this. The way you prove this, and remember, we can't just pick an epsilon because we got to prove it for every epsilon greater than 0. We're going to have to find, the trick is to find a delta in terms of epsilon. So no matter what epsilon you choose, you're always guaranteed to find a delta that works. If you remember in the simulation, we said I can make this epsilon as big as I want it, bigger or smaller, but I'll also have to adjust my delta to be able to make it work. So then how do we do that? For all epsilon, we're going to start by, the way we prove this is we're going to start initiate epsilon here and say let epsilon be greater than 0. And we sort of going to work backwards here. So remember what we had in the definition here. We want to make sure this is true. In order to prove this limit exists and it's actually equal to this L, we want to make sure this implies that. So we're going to work backwards to be able to find this delta, right? So we'll start from the end here. F of x minus L less than delta, epsilon. So we write it in here. All right, so the idea here is to try to work backwards from here, from the end, and try to make, from the end here, try to make this fit into that, so that way we can involve delta in here with our inequality with epsilon. So we take this right here. Okay, well, let's simplify a little bit. 2x minus 4 less than epsilon. I can factor it 2 out, and this 2 in front can come outside the absolute value because it's just a positive number. So we can have 2 absolute value of x minus 2 less than epsilon. And here it is. Now from here, I can simplify and isolate this absolute value, x minus 2. I divide by 2 on the other side, and I get epsilon over 2. Notice here I get my epsilon over 2. I already had that epsilon over 2 is less than delta. So then this gives me the intuition to go ahead and, from here, I can see, oh, okay, well, this has to be less than delta, and working this out gives me epsilon over 2. So why don't I choose my delta to be equal to epsilon over 2? This way, now I work backwards, but to prove it, to show that this is actually true, remember, we have to show that, right, for all epsilon, there exists a delta such this implies that. But now that happens now, because this right here, x minus 2 less than delta, but remember delta is equal to, I chose my delta to be epsilon over 2. This implies that the function f of x minus L, I'm going to write it with the symbols here, is less than delta. But remember what my function was? I've already worked it out here, but I'm going to do it again. A function was 2x minus 1. Sorry, 2x plus 1 minus 5 less than epsilon. Okay, is this true? Well, let's see. I mean, we've already done it over here, but let's redo it again. This is 2x minus 4 less than epsilon. We factor the 2 out, and we can get that 2 out of the absolute value, and we get this. Now, but remember we said this is less than delta. So then this has to be less than 2 times delta itself. But delta, we said, is epsilon over 2, which is equal to just epsilon. So this shows that this, in fact, is less than epsilon. So notice here how we didn't use any numbers. We derived a delta in terms of epsilon, so no matter what epsilon is, we're always guaranteed to have a delta that works. So in other words, remember how we did one with numbers here? Okay, we showed it there, but if we made this bigger or we made it smaller, we had to choose a smaller delta. Well, this guarantees that you always have, remember the theorem says, or the definition here says that we only need one. There exists one delta, but it's got to work for all epsilon. So if you let epsilon be whatever you want, just 5, right? If you let epsilon be 5, then this will be 5 halves. The delta would be 5 halves. If you let it be 1, this will be 1 half. If you let epsilon be as small as you want it to be, delta would always be half of that. So you're always going to guarantee to have a delta. Now remember, there could be more than one delta that works. I mean, definitely a smaller delta would work in this scenario, but it's only sufficient to find one to be able to prove that the limit exists. I want to show you quickly a simulation, just a quick example of something similar to this example here on what would happen, how would a neighborhood of delta and epsilon look like for a function where the limit fails to exist. So if you look at this problem right here, right, look at the 2 and the 4 there, similar to the problem that we had, the first problem that we had where we showed that one of the cases where the limit fails to exist. Here, as you come from the left, the limit as x goes to 0 is 2. But as you come from the right, the limit is 4. So this is a typical one of those cases where the limit doesn't exist. So how do you show that with the epsilon delta? Remember, it's easier to show that something is false than it is true. We just went through a whole formal definition with the epsilon delta to show that the limit actually exists. In this case, it's a little bit easier. You just have to find one epsilon for which you're not able to find a delta where all those points is going to fall in that neighborhood, in the neighborhood there. Okay, so here it would suffice to just find one epsilon where no matter what delta we choose, we're not going to fall. There are going to be some points in the neighborhood of delta, regardless of the delta that we choose, that are not in the neighborhood of epsilon. So here, if we move the epsilon here, now let me move this point here. So I want to make it so that the c is 0. Okay, so I'm making the limit point be 0. So we're taking the limit of this function as x goes to 0. And I'm going to make this epsilon 0.5 right now. All right. And I'm going to make this delta, I'm going to start with big here. I'll make it 0.5 as well. You see all these points right here in the neighborhood. Okay, so you can clearly see here how any point on this neighborhood, in this red neighborhood, right, doesn't fall in the blue neighborhood. So all of these do, but notice how all of these are not, they're outside the neighborhood of epsilon here. So remember, the blue part is the neighborhood of epsilon. Now you say, okay, well, why don't you choose a smaller delta? Okay, well, let's do that. I'm at 0.5. Let's go all the way to 0.2. 0.2 is right there. Okay, regardless, I still have, all of these are in the neighborhood of, right? Look at this half, the right half of the neighborhood of delta here. They're all in that blue neighborhood. Yeah, those are fine. But then this right here, right? This part of the function is outside the neighborhood of delta, of epsilon, I'm sorry. So it keeps failing, right? And remember what we talked about, no matter how close you get, I mean, you can always zoom in here. Regardless of how small I make this delta, I keep making it smaller and smaller and smaller, really small. I'm always gonna have some points in here, even if your eye fails to see it. The smaller you get here, I'm always going to have more infinite amount of points that are not part of the epsilon neighborhood. Again, regardless of how small I get, right? I keep getting smaller, but I still have points in there, and I keep doing that forever and ever. So I'll never be able to find a delta that works for this particular epsilon. But I don't have to even show it for all epsilon here because it fails for one. And remember how the definition said it has to work for all epsilon. So if I'm trying to disprove something or show that something is false, it's enough to just show that it doesn't work for one epsilon, since it has to work for all of them. So hopefully, guys, this give you the intuition that you need, not only informally but also formally here, for this idea of limits. We're going to be using limits from now on and moving forward. And remember how in the previous section we saw how we're going to need this tool, this limit process, to be able to understand the tangent problem, be able to solve the tangent problem as well as the area problem, and from there develop our differential calculus and our integral calculus.